So we're now ready for the next talk from Roberto Longo from the University of Rome, tour Vergata. It will be on entropy and the modular Hamiltonian.
Morning. I am very glad to be here in this wonderful place. I want to thank the organizer and of course, in premise, to Jeffrey for this kind invitation. The talk here. So quantum information is now a fast-growing subject. It's quite famous. And let me say that one of the problems, the main problems in the quantum information is to describe the information carried by a quantum channel when Alice and Bob communicates the content of the information or the storage of the information. And if you look at the literature on quantum information, you see that the most of the literature is dealing with the finite dimensional systems. This is certainly good in the sense that in practice we have only finite dimensional system with a finitely many degrees of freedom. However, it is unsatisfactory from 2 points of view. So mathematics, I am an operator algebraist. Well, one is wondering why to restrict to finite dimensional systems. And on the other hand, there are situations in physics, also famous situations, where infinite dimensional systems occur. And if you want to apply quantum information in the setting of quantum field theory is intrinsically dealing with the infinitely many degrees of freedom, because there is particle creation, annihilation, so the number of particles cannot be bounded. And in the past, in the 60s and 70s, so there was this Bekenstein working entropy description of a black hole. This is, of course, it's a very physical deal, but not mathematical, but it deals with the infinite dimensional systems. So I think it is good to try to give a solid basis to quantum information for infinite system. So what is the natural language? The natural language is the language of von Neumann algebras. What is a von Neumann algebra? Von Neumann algebra is you start with the Hilbert space, complex Hilbert space, and we look at all bounded linear operators on this Hilbert space. This, of course, linear space is an algebra. There is a star structure, so it's a star algebra. And one looks at the subalgebra, star subalgebra, which are closed in the weak topology, the natural topology, or equivalently, the algebra that coincide with the double commutant. One, take M, subalgebra, take all operators that commute with M, the commutant, and all operators that commute with the commutant. And this double commutant is a closure by the famous theorem by von Neumann. So if we look, if we specialize to commutative subalgebras, well, it's well known that the M von Neumann abelian subalgebra is just L infinity, in the sense that Hilbert space can be L2, and the algebra is the algebra of operator multiplication by L infinity function. So von Neumann algebra is just non-commutative measure. What is the interpretation in physics? The observables are the self-adjoint elements of the von Neumann algebras. The states are normalized positive linear functions, which are weakly continuous, so it's a continuous in a normal in a initial topology, and phi of x is the expected value of the observer x in the state phi. So if we look at thermodynamic or statistical mechanics for the moment for a finite quantum system, so we have a matrix algebra, an Hamiltonian H, an evolution. The Hamiltonian gives a unitary evolution, and the adjoint is an evolution on this matrix algebra. And it's well known, the equilibrium states are the Gibbs states. So they are given by the trace to E2 minus beta H normalized. It's now, if we want to have something like this equilibrium state for infinite system, we of course this definition cannot work because there is no trace, and also the evolution is in general not inner. So in 50 years ago, we proposed this replacement, the K-mesh condition. So if you have a sister algebra, so it's just a phenomenal algebra, or a phenomenal algebra if you want to just, and then one parameter automorphic group, tau, and the state phi is said to satisfy the Kubo-Martin-Schwinger condition at inverse temperature beta. If we take the 2-point function and we reverse under the state, then these two values are boundary value of an analytic function on the state. No? So if the evolution is trivial, it is just a trace. So it is a sort of commutativity after analytic continuation. And if you apply this definition to the matrix algebra, you recover the Gibbs state. So this is good for infinite systems. Now, at the same time, Tomita-Takesaki, about 50 years ago, they make a true breakthrough in the setting, the subject of phenomenon algebras. So take a phenomenon algebra, so it acts on some Hilbert space, and we can assume the state is expectation value with the state, a normalized state, or let's say, which is a cycling and separating in the sense that if we apply the algebra to M, we get dense set, and also if you apply the algebra to the commutant to the state omega. And then we can identify the algebra by taking an operator and apply to the vector. The algebra is identified with the dense subset of the Hilbert space. But then on the Hilbert space, the star operation is no longer isometric. And so we have an operator. This operator is antilinear, right? It's closed. And by the standard procedure, the polar decomposition, one can write this operator as just an anti-unitary evolution and dealt in the square root of a positive operator. And the truly remarkable discovery of Tomita-Takesaki is that if you exponentiate the logarithm of delta, this implements an automorphic group. And J is a reflection. It's a reflection between the algebra and the commutant. So the moral is that given every state phi, we have an evolution. No? So when we are in a classical situation, we have a space, and then we put an Hamiltonian by ends. But here, the states determines an Hamiltonian. So the logarithm of delta is a generator of a symmetry. And this symmetry is truly remarkable. Among this modular group, let me recall three properties, which is the modular group is purely non-commutative. So if you look at the commutative case, it's just the identity. So it counts on the quantum level, but it's not existing in the classical level. It's characterized by the K-mesh condition. And the third property is that it does not depend on the state up to inners. No? Every non-commutative phenomenon has a lot of inner automorphisms, but the two states the modular group of two states are equivalent by a conical cycle, so up to inner automorphism. Okay. So the generator of the modular operator is called the modular Hamiltonian. Of course, one can embed the two states, different embedding, and take what is called the modular Hamiltonian attached to two states, relative to two states. And this object is now considered, it's an hot topic in physics. So if you digit modular Hamiltonian on archive, you get a lot of papers with this. So let me remind you the notion of information entropy. So we have a finite set of events and x1, xn, and the event xi occurs with probability pi, and then the Shannon entropy is the average of the, so the information is a log of pi because it should be additive, while the probabilities for independent events is multiplicative. So the Shannon entropy is the average of the information with this probability space. And the relativity entropy is just a measure. If we want to measure the information, but we are in a wrong state, slightly wrong, then we take the average of the difference of the information. And this notion can be done in the non-commutative case. So von Neumann defined the entropy, which is the generalized Shannon entropy, which is you have a state given by density matrix with respect to the trace. So the phenomenon entropy is traced to rho log rho, and Umagaki generalized the notion of relative entropy. So it is in an infinite quantum theory for a general phenomenon, there is no trace, so it is not possible to define this the relative entropy. But Araki could define the relative entropy in general for arbitrary states of phenomenon algebra, just the expectation values of the modular Hamiltonian in the second state. And this has all the good property. It's a key concept. It is always definable. So I take the point that the relative entropy is the true primary object. All other concepts can be defined in terms of relative entropy. Now look at the phenomenon algebra. Phenomenon algebra with trivial center, a factor. No, the center is the classical part. There is no classical part. And then Müller and von Neumann classified, dividing in types, phenomenon algebra. Type 1n means d of h with on a space of dimension n. Type 2 means that it is a threshold state, but it is infinite dimensional, so it's a continuous trace. To infinity, it has a trace which is not everywhere defined, like the trace in d of h, but it's continuous. So it is a type 2-1 tensor, type 1 infinity. And type 3 has no trace at all. In fact, two non-zero projections are equivalent. Alan Kohn in the 70s divided type 3 by modular theory into type 3 lambda in 0-1. And type 3-1 are the ones that most occur in physics. Now, if we look at the quantum field theory, like the phenomenon algebra or the observer associated to some region O, that is typically type 3-1. So phenomenon entropy is infinite. However, there are two ways to handle with this. One is to take a slightly larger algebra region, and in the middle, one can find a type 1, and then compute the entropy with respect to type 1 infinity factor. And this was recently shown to be finite in a lot of models by Feng Shui and myself. And then one has to let these two regions shrink together and see how it diverges. Or another approach that the approach in my talk is to study the relative entropy of any state with respect to the vacuum. This will be finite because the ultraviolet divergences are subtract. Now, I will talk about something very elementary, standard subspace. So take a complex Hilbert space carrying H and a closed real linear subspace H. Then the symplectic complement is all the vectors which are orthogonal. Imaginary part is between psi and H is 0 for all vector x eta in H. So it's the real orthogonal or IH. And we can assume that it is cyclic, so the complex span is dense and separating the intersection. So OH into intersection with H and IH is 0. Otherwise, we throw away this part. It's a standard space. And then we can define this operator from H plus H to itself, psi plus I eta to psi minus eta. It's an involution. This is S operator S, and the adjoint of S of H is just S of the symplectic complement. And we can decompose it in polar decomposition, and we have a sort of one particle situation for the Tomita-Takesaki structure. So the logarithm of delta gives one parameter group of symmetries, and J is a reflection of H symplectic complement. This is much simpler than the original Tomita-Takesaki theorem, but on the other hand, there is no phenomenology here, so it's a structure that can enter in many places. In the end, I want to give you the key concept of this talk, which is the entropy of a vector in a complex Hilbert space, a vector K, with respect to a closed or real linear subspace H. The formula is the following. It's the expectation value I, the modular Hamiltonian of H, with the P of H, which is a cutting projection. So the projection that if we decompose a vector in a part in H and a part in the symplectic complement, and then we drop the part in the symplectic complement. This unbounded projection. This is a real linear operator because P of H is real linear, but so it gives a real linear positive operator, which is called the entropy operator, and the entropy is just the expectation value of the entropy operator. So these are all the nice property, good property of the entropy. It's a positive, it's monotonic, Lauer-Zech continuous under monotonic approximation. It's a finite for a dense set of vectors. So we have the notion of entropy, and now it is good notion because if we go to second quantization, we get a phenomenology, and this entropy will give the entropy, Arakis entropy in a second quantization of the coherent states. So what we have in quantum field theory, first we have a fair quantization. So for every region, we get a real linear space, and then we quantize. So we are in a first quantization. So we have a map for every region. We have a real space of a real linear subspace. We should think in the following sense. The Hilbert space is the waves, so all waves, and the A overall are the waves with Cauchy data localized in here. So the problem is Alice is sending a message to Bob, and Bob can measure this signal only in a limited region of space and time. And then I want to define this entropy, the entropy of the part that we measure. So the entropy of the wave relative to the region. And so wave, or more general for Klein-Gordon, it's a solution of the wave operator, more generally of the Klein-Gordon equation, if there is some massive. And then we want to define the entropy of a wave with respect to this certain region. And okay, and by definition, the entropy of a wave in a certain region is just the entropy of phi with respect to the subregion or subspace corresponding of wave localized in the region O. And then for half plane or a wedge in a space-time, one can compute, and this is a formula. This is the energy given by the stress energy tensor, and the wave is given by this formula. And what is important is that, of course, one can compute the derivative, but the second derivative of the wave when we move in a null direction is non-negative. So for a general system, of course, the entropy is positive. If you go to subsystem, the entropy is lower. So the first derivative of the entropy is negative, but there is no reason why it should convex. So to say the second derivative should be positive, but it is true. And it is related to the quantum non-energy condition that I will show. So this is the abstract result, no? That maybe I don't have time to illustrate, but it's just the fact that if you have a one parameter group with positive energy, it's a standard subspace into itself, then we can compute the entropy with respect to the translated subspace, and then the second derivative is non-negative. So it's an abstract result that applies in many contexts. So, for example, in a curved space-time with a bifurcated Killian horizon, for example, then we have the state we can translate the wedge, like the Schwarzschild space-time, for example, and then the entropy is non-negative. And now that was for half space. For a ball, let's say, then this is the formula of the modular Hamiltonian in terms of Cauchy data, and so it's a multiplication by the parabolic distribution, and there is the other diagonal term is just higher dimensional Legendre operator. So one can compute also the entropy or the density for a wave massless in terms. This is just the formula where you see that there is this stress energy tensor part which appears, which is physical, but there is also the integration of the square, which is a Born type term. There is a connection that I had no time to explore, which was quite intriguing, with the Perlite operator that recently Alan Cohn is considering, because then the Perlite operator is this operator here that appear in a quantum communication, and then the entropy of a wave is just the expectation value of the Perlite operator plus 2 terms of Born type. I have no calculation, no, I cannot say anything about the meaning, but it's certainly quite interesting that this so cool. in the remaining part, I want to mention my recent work with Edward Witten. Edward Witten had this idea that the phenomenal algebra in quantum physics are of type 3, but there is a procedure due to Tomita-Takesaki of considering the cross product by the modular group. The cross product is just a sort of semi-direct construction. And by this cross product, one gets a type 2 infinity phenomenal algebra. And Edward Witten considered a certain states on the cross product, which is where the Hamiltonian is a deformation of a perturbation of the modular Hamiltonian, and interpret it in terms of black hole entropy states. So, motivated by this, we recently studied this notion of type 2 entropy. So the version of phenomenal entropy with respect to a trace which is not a continuous trace. And we got this estimation that when we go to subsystem, there is a bound by the increase of this continuous entropy by the logarithm of the joints index. This continuous entropy was considered in 1960 by Siegel, but I think nobody considered, up to my knowledge, in the sequel. One of the reasons is that, of course, the algebra in quantum physics are usually type 3, but there is another reason, presumably, that in the classical case, this continuous entropy corresponds to the notion of differential entropy. That has some problems because it is not, it's due to Shannon, because if you approximate with the finite system, you don't get a differential entropy. But it is important, but if we properly renormalize the approximation by finite system, we get this approximation. So this is good. And there are many things that I could not talk by time. One maybe among the many results that I could mention, maybe since I have 1 minute, I will say something on this one, the Landauer's bound. Landauer's bound is a lower bound on the physical and information entropy of a system, and it is given by the Boltzmann constant to the logarithm of 2. But when we go to infinite system, we get 1/2. So it's a new bound. And the reason is the following, that the Jones index values, the values of the Jones index are quantized. So the first value is 1 and the second is 2. But when we go to finite system, to matrix algebra, the first value is 1 and the second is 4. So in infinite system, also the bound 2 can occur. So it is a new phenomenon that occurs just by looking at infinite systems. Maybe I'll stop here.
Thank you very much. So we still have
6 minutes. Yes.
great talk. I just wanted to ask whether, as in the finite dimensional case on your last page, we have equality for some phi. Have you studied that equality too? So in this last inequality.
The bound is optimal for infinite system. For finite system, the index, it is almost depends on the ratio of the dimension. For smaller ratio, it is not optimal.
So my student actually studied that question and we proved the paper. So in some cases, this is known.
In some cases, finite dimensional cases, not.
Well, you know, he has to get a job in quantum information, so
Oh,
he did
okay.
it in finite.
And this is related to the what called quantum uncertainty relations.
Mhm.
Yeah, that's just studied in the physical research. So it's a
Could I ask about the relation to black holes that you mentioned? Because my understanding is that black holes are well modeled by a finite dimensional Hilbert space with a qubit per 4 Planck squares. So why do you need type 3 algebras?
Oh, because if you want to study with in terms of quantum field theory, so you have a space-time and you observe, then it comes automatic. Quantum field theory, as I said, you are by intrinsically infinite dimensional. You cannot put a bound on the degrees of freedom, so you get infinite.
But the Bekenstein-Hawking formula for the entropy of a black hole is a finite quantity. And I was
Yes,
interpreting
it's a
that as
finite
essentially
quantity.
the number of qubits.
If it's a finite quantity, yes, but that's a qubit. This is their description, but I don't think this is a rigorous description. Of course, it's physically very meaningful, exciting, but I'm looking for something rigorous to give a rigorous basis of this analysis, and then you cannot stay in the finite dimensional context. You are forced to be in the infinite dimensional setting.
Yeah, I agree. Consider the entire field theory. Okay.
Hey, Professor, can I have a question? I just see that you say the relative entropy between the state and the vacuum state is finite. So is that the infinite entropy is always from this vacuum state, and is that the vacuum state we have infinite many entangles so that we have those infinite entropy?
No, the relative entropy between a state and the vacuum could be infinite, but for the dense set of state is finite. But the point that okay, I had no time to discuss this, but there is an important conjecture in physics that in physics the situation we know that classically the energy is positive. That we know very well. When we go to quantum field theory, the local energy is not positive. This Arthur Jeffrey and others discovered many years ago. So what is it? On the other hand, if you want to quantize, let's say gravity, which is we don't know how, but in any case, we need a notion of positive energy. And the proposal is that for physics is a quantum null energy conjunction, which says that the relative entropy between any state and the vacuum, when we move the subsystem in the in the null direction, the second derivative is non-negative. They have physical argument that I don't understand, not rigorous, but they have physical argument for this to be equivalent to the positivity of the energy in the null direction. And but there is this problem to prove this. Best result probably is due to Sealand and Faulkner that prove for a dense set, but we need all. And we have a rigorous proof for coherent set. For all coherent set is true by this by the structure that I have mentioned. But the full conjecture is still open.